welcome back to the 19th lecture of this series. So, previous class we talked about a comparative analysis about Raman spectroscopy and IRS spectroscopy, and let's recollect some of the facts what we talked about. When we talked about Raman spectroscopy, the common feature, both of them, they are both vibrational spectroscopy, and both of them is the signature of the vibration of the atoms. The basic fundamental difference is in IR spectroscopy, light is absorbed by the atom and that leads to the vibration, and due to absorption it leads to a change in the dipole moment. On the other hand, in the case of Raman spectroscopy, what happens, the light is scattered and the scattering causes a vibration, but it changes the polarizability of the molecule. And what we have observed is you can use for heteronuclear functional groups, IR spectroscopy is more favored, whereas for homonuclear groups Raman spectroscopy is more favored. And both these techniques are complementary to each other. They walk hand in hand, and in order to get a complete picture of any material, you have to have an overall idea about both the tools and their limitations. Further, when you couple them with AFM, you get an overall picture about how they are distributed on the surface, how they change their electrical properties, as we will coming in the next class about it, and how their oxidation reduction potential alters, and all such informations. Having said this, so in this lecture, which is 19th lecture, we will talk a little bit about the applications of Raman spectroscopy, because this is one of the very powerful tool in modern analytical chemistry. So, if you look at the pharmaceutical industry, then you will see light stability of ciprofloxacin tablets, xanthine derivative tablets, quinone derivative, antibacterial tablet, theophylline hydrates, anhydrate, crystalline polymers, and so on and so forth. There is wide array of its application. Right? Okay. Similarly, if you go into the food company, where chocolate surfaces, emulsion imaging, component of egg yolk, thermal changes in trehalose, dehydrate, fatty acids and food oils, lactose, multilayer films or packaging, all these things are feasible. For the carbon material, you can really figure out most of the carbon allotropes, powder semiconductor, crystallinity of polysilicon. For electronic devices, foreign matter in liquid crystal substrate. So, in a way you can really figure out the dopants in it. In the polymer compounds, 3D imaging of cellophane tape, polypropylene, and all these things you can do. Similarly, in the biological material of our important visualization of C island structure in blended polymer, structural change in protein, this part is of extreme significance for us. Structural changes in proteins, hemoglobin, lysozyme, cytochrome C, enzyme ribonuclease A, dental adhesion collagen, chemical imaging of coral structure, orientation and evaluation of spider silk. Both spider silk as well as the mulberry silk, you really can get a very good visualization. In the cosmetics industry, mostly all the makeup tools could be used, their component could be detected. For the gas, natural gas hydrates and others, there are wide array of applications out there, which is beyond the scope of this course. But what is important for us to understand, why it is important that you understand the very basic of this spectroscopy specifically. This is something I really want you people to. In the last class I discussed about it, I didn't go into huge details of it, but here I am again revisiting it. And you always remember, this is IR, where if this leads to change in the dipole, and here you have change in the polarizability. And if you look at it, most of the compounds out here, the signatures are better for all the homonuclear complexes, and here you see in the IR, this is the zone. And this is extremely important that you guys kind of try to have a mental map of this particular slide. You have the bending vibrations, which are shown for these ones, and you have the stretching vibration, which are shown for this one. So you could see the bending vibrations are only kind of in this zone, whereas stretching vibration is all across the spectrum of it. Okay. So next part is when Raman is coupled with imaging tools. Now, when we talk about imaging, say for example, you have a sample and you know it has, or you guess that it has some unique chemical signature. How to go for it? One of the ways to go for it is you have a microscopy, you have a AFM, and you have a spectroscopy. When you couple a microscope with a AFM with a spectroscopy, and you get a multimodal resolution of something like this, where these red are these spots, what are you see? These are the anatase crystals, titanium dioxide nanofibers, which are present there, and you really can image the whole thing. So you see the power of the tool. So this is the resolution level. Now you can even further go down, you can even figure out how this titanium dioxide is arranged in a geometry, what is the shape in 3 dimension. As of now, what you see is the 2-dimensional aspect of it. But then using the power of AFM, you can probe this side and you can figure out that how this whole structure is really formed in 3 dimension when you could recreate it. So you realize that when we are coupling these techniques, we can get a fairly good resolution of all these things. Now, having said this, the next important aspect, which is of extreme importance for those of you who desire to shape up their career in biosensing, they have to realize that what kind of laser you are going to use. That is of extremely important thing. Laser selection for Raman spectroscopy, because it's not that every laser will work for everything, right? So if you look at the application side first, fluorescent sample, resonance Raman, and biological samples, they have a particular area where you can use them. Okay. Ultraviolet, these are for resonance Raman surface measurement and photoluminescence, and fluorescent biological samples. So mostly if you look at it, these are the kind of lasers what you have to use. Depending on what kind of sample you will be dealing with, you have to pick up the laser, and you have to be really careful while you pick up the laser, because there are several aspects. So if you want to go at this zone, it will come with its own set of features. If you want to be in this visible zone, it will come with its own feature. The ultraviolet zone, which is high energy lasers, so that will come with its own set of plus and minus. So laser selection in Raman spectroscopy and as well as in IR, they are extremely important. So challenges what Raman faces. Raman spectroscopy comes with a very interesting challenge of fluorescence problem. There is always the issue of interference with fluorescence, and there are different ways how fluorescence can be removed from Raman spectroscopy. Otherwise, it becomes a very noisy signature, and many a times the user kind of refrain from using Raman. Oh, there will be a lot of fluorescent problem and likewise so on and so forth, but that's not an issue. If you are clever, you can get rid of the fluorescence. So let's explore. Fluorescence can be a side effect in Raman measurement and can originate from either the target molecule or from the surrounding matrix. Care must be taken if sample is contained in a vial or tube, as this can also cause background interference. So be very careful with these things. There are two physical methods of reducing fluorescence. The first is to select a laser wavelength at which fluorescence does not occur. So that's why this part is very important, that you understand which one of these lasers won't cause any form of fluorescence, because you have to really get rid of this fluorescent part, right. This is typically a longer wavelength where there is insufficient energy for electron excitation. If you remember, I was telling you, so if you come here in these kind of lasers which are longer wavelengths, then that energy will not be sufficient to allow an electron to jump out. But if you use high intensity UV lasers or something like this, then lot of electron, because they are very high energy, right. So lesser the wavelength, more will be the frequency, and these are those wavelengths where we are dealing with. So they will have a pretty high energy, right. So you have to be careful that what kind of laser you are selecting. So there is insufficient energy for electron to be excited out. The second method is to choose the aperture size and shape to mask as much of the sample matrix as possible to eliminate the matrix fluorescence. Well, this is a very interesting technique. If you think of it, what you are trying to do is, okay, you are not bothered about the laser, everything is fine. You are just minimizing the aperture. It's almost like you are using a camera, you are changing the shape of the entry of the light so that you are almost focusing at one point, such that you do not gather the noise from the surrounding. As a practitioner microscopist, I can tell you this only comes with experience. There is no shortcut to this one, and this is a very tricky technique. Those who keep on trying, keep on playing with it, they do it, but it is not easy. It's truly not easy, because controlling the aperture, getting the right sort of picture, exactly what you are looking forward to, it demands a lot of practice. Unless you really play with the lenses and the laser in a right way for a prolonged period of time, you really will be at loss at times. So you have to be extremely careful when you talk about this. Second method is to choose the aperture size and shape to mask as much as of the sample matrix as possible to eliminate the matrix fluorescence. So it is something like this. Say for example, this is your sample, okay, this is the matrix and here is your sample, right. So now I have to ensure my laser beam is almost like this, so that I am not picking up anything from the matrix which otherwise will give the fluorescence. And this background fluorescence is very common. I have observed people who worked on hydrogel, cryogels, I have seen that they have an inherent autofluorescence, and it's a big challenge for those researchers to get rid of that autofluorescence. You cannot get rid of them so easily. So the only way you can do is focus the laser so much on the biological exactly sample that, and of course then you have to do it very fast. You cannot prolong it, eventually that will get damaged. The second method is to choose the aperture, what we have talked about. This is improved with dual spatial filtration, DSF, included with NRS of 5000 to 7000 spectrophotometers. The third option is to use a fluorescence rejection algorithm. These algorithms which are there in the market, but they are mostly patented and highly effective at removing broader fluorescence spectrum, leaving the sharper Raman peak with a clean baseline as shown in the next slide I will show you. But the problem with much of these algorithms are that everything is happening in your backhand. You really do not know what you are getting rid of, because the person who writes algorithm is writing it with certain baseline values, but that may not be your baseline, right? You may lose certain signals, because whenever we talk about the filters, they pick up certain value and set a baseline that anything below this they will cut, they will filter it out. But when you are dealing with unknown samples, it is kind of can become misleading at times, because you may get rid of a lot of signals which were there, but one has to make a choice. To summarize here on the slide, what all the options you are left with is, first to select a laser which will be low energy laser, okay, so that you will not eject any electrons, so that they come back and fluoresces while they are coming back to their shell. One way of doing it, low energy laser. Second one is you are focusing on your target using the aperture, and the third one is the algorithm based system. Okay. So there is no one way to do this. Again, this too will be a multimodal option of application. Now, when you look at how the fluorescent correction can be performed during post acquisition, is this is how the aqueous spectra looks like whenever you look at it. So, say for example, you send that to a reviewer, they will say do a baseline correction, and this baseline correction is nothing but you are getting rid of all the noises which are present, and when you report the result, this is something what you is in the red trace what you see. This is how you report a Raman spectra, which will tell you that what kind of functional groups which are present there, and what kind of molecules which are moving on the surface, okay, or vibrating on the surface. So this is what spectra looks like once you clean it up completely. So once again, going back to this slide. So this is what is of key importance. That's why I am getting back to this slide multiple times to tell you that keep this slide in mind and keep these two concepts in mind. And whenever we are talking about anything to do with matter and light interaction, you have to realize there will be those 5 different situations. There will be scattering, there will be reflection, there will be refraction, there will be absorption, there will be vibration, and this absorption will lead to, if it is a high energy laser, then it could lead to fluorescence, photoluminescence, and all other different kind of situations, because the electron is moving. Because all these things are very simple as long as you can close your eyes and you can visualize when the light falls on a material, how the material or the atoms alters. Scattering, we talked about that, SNOM. We talk about reflection, we talk about refracting, where the light is passing through, absorption, vibration of atoms, we talk about the Rayleigh scattering, and then we talk about, if you go back, yeah, we talk about the Rayleigh scattering, we talk about the Raman scattering, Stokes and anti-Stokes, where this is the original wavelength and here you have an increase in it and there is a decrease in it. So, there is a anti-stoke which is basically adding it up, and there is a stoke which is subtraction, V0 minus V. Okay. So, and then we talk about the IR spectra. So, this is overall is when we talk about, and one more thing worth remembering is homonuclear and heteronuclear complexes for Raman and IR based systems, and the degree of polarizability as I have talked about for Raman spectra. And in terms of the applications, to realize that they are used for structural changes in protein, hemoglobin, lysozyme, cytochrome, and all different kind of viruses, spider silk, as well as your basic mulberry silk and all other different kind of proteins. And they could be used for detection of wide range of pharmaceutical agents which are present there, contaminations of foods which can be used, and mostly all different kind of polymers and biopolymers which are being used. And we have already talked about a multimodal imaging by coupling AFM with microscopy and spectroscopic techniques, where you really can detect what kind of atoms which are present on the surface, and you can rebuild the three-dimensional geometry of them. And then we talk about the lasers, and we talked about that if you use a low energy laser, then your chances of minimizing fluorescence is higher versus a high energy laser, where it will eject electron, and that electron, once it ejected out from its surface, will take its own course to get back to its ground state, and during that time it will give a lot of fluorescence, phosphorescence, photoluminescence, all sorts of signatures out there. Okay, so you have to be careful with it. So, what kind of laser you are picking up? And then we talk about challenges of removing the fluorescence from Raman spectra, and here we talked about how you could do that by selection of laser as well as changing the aperture or using certain algorithms. And here we finally talked about how the final spectra really looks like. So, I will close in here and I will move to the next lecture after this. Thank you.